Hello, 8th grade. We're going on to the next section of science in chapter 4, which is 4.14, and we're going on to circular motion. So far we've talked about forward motion. Last time we talked about Sir Isaac Newton and his laws of inertia and gravity and forward movement. And so today we're going to move on to circular motion, things moving around, and what kind of force that causes. So objectives: identify force and motion of a circular path, correlate centripetal acceleration to Newton's laws. Some vocabulary: centripetal acceleration is the change in velocity of an object traveling in a circular path. Centripetal force is the force that continuously pulls objects traveling in a circular path towards the center of a circle. So let's start reading. Newton's first law of motion, the law of inertia, states that an object travels at a constant velocity unless an unbalanced force acts on it. So an object in motion stays in motion is basically what that law says, unless there are other factors like friction or gravity that cause it to slow down or speed up. Velocity includes both speed and direction. Since maintaining a constant velocity includes traveling in a straight line, how can Earth orbit the Sun? Why does Earth not travel in a straight line? Does circular motion violate Newton's first law of motion? The answer is no. An object's inertia maintains the object's speed, but a force acts on the object to create a circular path and to keep it from traveling in a straight line. The force that continuously pulls an object in a circular path towards the center of a circle is called centripetal force. It is always perpendicular to the velocity of an orbiting object. If you tied a string around a tennis ball and swung it around a circle around your head, the tension on the string would provide the centripetal force that pulls the ball towards the center. But if that string snapped, the tennis ball would not keep traveling in a circle around you. It would fly off in a straight line in the direction that its velocity was heading in the time the string broke. A force must act on an object to keep moving in a circle. For instance, the force of gravity becomes the centripetal force that holds the planet in its orbit. If an object is moving in a straight line, its changes in velocity are the result of a change in speed rather than direction. But this is not true of an object moving in a circular path. Even if the object is moving in a circular path at a constant speed, its velocity changes continuously because its direction is constantly changing. The change in velocity of an orbiting object is called centripetal acceleration, and it always points to the center of the circle. If the object is traveling at a constant speed around a circle, the total acceleration also points to the center of the circle. If an object is speeding up, the total acceleration points in the direction of the object is moving. If an object is slowing down, the total acceleration points back, away from the direction the object is moving. Consider how an artificial satellite or space shuttle stays in orbit around the Earth. A satellite is continuously pulled toward the center of Earth by gravity. To set up a stable orbit, the centripetal acceleration needed to maintain the orbit must be exactly equal to the attraction of gravity between the satellite and Earth. Through careful calculations, scientists can launch a satellite into orbit Earth at exactly the same rate that Earth rotates. Although the satellite is orbiting, it seems at all times to hover over the same point above the Earth because it's orbiting at the same rate. So as we turn, as the Earth rotates, so does the satellite at the same rate. Why do astronauts in space appear to be weightless as they float inside their spaceship? It might be assumed that astronauts are so far away from Earth that there's no gravity pulling on them, but that is not accurate. Gravity is still acting as a centripetal force. The astronauts appear weightless because they are in free fall, the condition of an object when gravity is the only force acting upon it, along with everything else in the spacecraft. If the cables of an elevator in a very tall building broke and the elevator accelerated at the same rate as gravity, the cargo inside the elevator would seem to float inside the elevator as if it were falling. So you might have seen this like in movies or cartoons where it has something dropping rapidly and everything inside slowly lifts up and kind of hovers in air until it hits the ground. So that's what's happening. It's when you have gravity is pulling you down, but there isn't that other force of friction holding you in a certain place. And so it seems like you're weightless. It seems like you're just floating with nothing. But it's gravity pulling without any other forces around you. So a Bible connection with this. David and Goliath. Before David faced Goliath, Scripture says that he chose 5 small stones from a brook. He then headed to the battlefield with the stones in his slingshot to meet the giant. King Saul offered David his armor for protection, but David refused it. David, the shepherd boy, was familiar with the power he could generate with centripetal force. He had used his slingshot many times to kill or ward off lions and bears that threatened his flock, and he knew the Lord was with him. On the day of battle, he confidently took his slingshot, loaded it with a stone, and began to swing it around and around over his head. As he continued to accelerate the stone, he was increasing the potential force with which he would eventually knock down and kill Goliath. When he achieved his maximum velocity, he released the stone, sending it in a straight line towards Goliath's head. The aggressor fell dead, and David had defeated Israel's army. So if you've ever, a sport that you can do in high school as part of track and field is called shot put. And you have this disc that you hold here and you spin around your body, spin, and then you throw it straight and try and get it to a certain distance. And so rather than like throwing a ball where you're standing straight and throwing it just with the energy from your arm, that is using centripetal force to pick up energy as your body rotates around to then throw it even faster. You see the same thing with women's softball. It's called a windmill pitch. And so instead of just pitching it underhand and letting go, they actually windmill or have their arm go all the way around before releasing the ball. And that centripetal force gives it an extra push rather than being able to just throw it overhand. All right. So some questions to answer for today. Define centripetal force. What does the law of inertia say about the motion of a moving object? What direction is the centripetal force in relation to the velocity of an orbiting body? What keeps an orbiting satellite from falling to the Earth? What is centripetal acceleration? And what keeps an orbiting satellite from flying off into space? So go back and look in the chapter to answer those questions. The lab for today, this is one that you probably won't be able to do unless you have the materials and want to try it. So things that you would need are a bicycle tire with a quick release hub or stunt pegs. So a quick release hub is where on your bike it has like a little lever that you push and the wheel just falls off or pops off. Or stunt pegs is if you have a bike that has like 2 pegs sticking out that someone else can stand on when you're riding. So if your brothers have a bike with those on it, you can try that. And you would need 2 oven mitts for stopping the tire. So basically what you're going to be doing is holding the 2 either stunt pegs or the quick release valves on your tire and spinning it and then moving it and feeling the force as it's spinning in centripetal force. The question is, how does a gyroscope help with stability? And so this is what it's testing. So if you have those materials and you want to give it a try, wonderful. And if not, that is okay as well. Next time we will come together for 4.15, which is Newton's 3rd law of motion. So think about it. A lot of time that Newton spent coming up with these theories was during a quarantine. So as we are sitting at home in our own quarantine, not nearly as severe as the bubonic plague that they were going through or smallpox for 18 months, we ourselves are in a quarantine where we are not allowed to leave the house. And so use this time to use your interests and things that you want to research more. You have extra time at this point to research it. And so do that. And who knows, you might be able to change the world through it. Have a great day, and I will see you tomorrow for Newton's 3rd law.